Good morning. My name's David Walker. I have the overly grandiose title of Field CTO for a database company called Yugabyte. Lesson 1 for today. Don't get carried away when you're writing your proposals for conferences. I was sitting with a colleague of mine. We thought we were being very funny. If you actually read the full description of it, it includes the line, heroic CSPs on fiery steeds with strong armor, flowing locks and facial hair rode to the rescue. Writing these slides became impossible with that theme. So, surprise, surprise, I used AI to generate the steed, and I'm not going to talk about Cinderella for most of the talk. The fairy godmother does make an appearance a little bit later on, but we'll come back into that. It'll be more serious. So today's conference is all about cloud native and modernization of applications. And really, this is a journey we've been on actually for the last 20 years. It's surprising how long these things have been there. Kelsey talked about Kubernetes upstairs. What we see this is in 3 big waves. The first wave was infrastructure modernization. That was what came with virtualization and then with Kubernetes and the containerization of those platforms. And that's largely been successful, although I was very interested to hear Kelsey say upstairs, and of course the next thing's coming along in a moment. So we saw virtual machines, Kubernetes replaced it, something else will replace it more efficiently underneath that coming forward. We then saw a mad rush into application modernization, microservices, producing stateless apps, all of those components. And what's really interesting about that is a lot of the architectures that you see out in organizations today have virtual machines or Kubernetes. They have the apps in Kubernetes, definitely. And then sitting behind them is either a virtual machine or a physical machine running a database which was designed in 1980. And yeah, we are doing an awful lot of work around that database. And when I say we're doing a lot of work, it's not just that we have a database. It's about keeping it up as much as the application is up. So if your database has been on a single node, you suddenly want to have high availability, 2 nodes, replication. You want to have different security parameters. You want to automate the deployment of that. All of these things have become challenges and things that we haven't particularly addressed. So what I'm going to do is have a quick look at where the database technologies generally are at the moment. The first group, there's 3 groups, I think, in this area. The first group is legacy databases. These are the ones that we're very familiar with. Postgres, Maria, MySQL, Oracle, DB2, and SQL Server. And there's some really great features about this. My personal history, I go back to Oracle 4, so I'm really ancient. But yeah, they give us that relational data model that people want. They give us ACID transactions. They give us strong consistency. And prior to working at Yugabyte, I was running enterprise data platforms for WorldPay. So we were doing banking transactions. All of those features were important to us. They were critical. If I'm moving your salary between one bank account and another, I kind of want to know that it's got there at the end of the month. Eventually, consistent doesn't really cut it for me. But what I end up with is the challenge of manual sharding, of trying to replicate that to another data center with an RPO which is very low, an RTO which is very low, all of these sorts of features. And increasingly, I'm struggling with geo-distribution. And with that, there can be lots of different aspects. Geo-distribution for protection of the system, i.e. in different areas in case something, the classic aeroplane hits the data center. But also geo-distribution in terms of compliance. So if you've got GDPR and you have to hold data in a certain territory, but you want to have a single database, how do you do that? The data center's in London. What about my European data? What about my US data? How do you start to manage these challenges across big databases? The next group are non-relational databases. Now, our founders, two of our founders, were the creators of Cassandra. So we know a little bit about distributed systems. They're very scalable. Yeah, we like Cassandra. It's incredibly scalable and fast. It's got native replication. You put 3 nodes in 3 data centers. It just replicates it. You do not have to worry about it. And it starts to address that problem of geodistribution. So you can build a database which is spread over three countries or 3 regions with it. To give you a feel for it, if you're in 3 regions in Europe on a data center, you can have 3 milliseconds as a sort of write time for a transaction. If you have a database which is built on Cassandra or ours, you're talking about 200 milliseconds for a write to have a database spread between Australia and the US and Europe. So it's actually starting to be viable. There's laws of physics which come in under this, but it's starting to be viable to get that data to be real. But in taking those non-relational databases and those SQL databases, you've lost consistency. You've lost indexing, and you've lost the relational model that a lot of the developers need for what they're doing. So it's great for serving layers of certain types, but it's not necessarily a strong thing for banking transactions, for example, with it. The third category is where the cloud service providers have stepped in. And they are starting to address this problem. So Google and Azure and Amazon are taking on the databases. There's Aurora, there's Spanner, and these sorts of databases are easy to use, and they're cloud native. They're available in your cloud service provider. So they're highly resilient. They are transactionally consistent and easy to use. But what you're starting to get into is another problem. Well, a couple of problems. The scalability is typically limited because of the way these cloud service providers have built them. Typically, it's one write node and many reads. So you focus all your writing into one location, and then it gets replicated very rapidly, transparently in the background. And if your node goes down, your write node goes down, another one has to come up somewhere else with it. So it's not actually truly distributed. It's one write, many readers. And increasingly, we see other challenges. So in the banking sector, there's something called concentration risk. And concentration risk is the idea that you've got too much in one cloud service provider. What happens if they have an outage? And initially, regulators started looking at this problem in terms of, look, Bank X has got all their stuff in Amazon. But now they're starting to look at this problem in terms of Bank X and Bank Y both use Amazon. If Amazon goes down, we've lost all the banking system. So this idea of cloud concentration risk is actually a huge challenge for people. The other thing that people don't want, and we see this increasingly, is to be tied to a particular provider and not have a solution for being hybrid. By hybrid, I mean the ability to run the same database on-prem and in the cloud, or even a database spread across between your on-premise and your cloud. So you've got 2 data centers traditionally, and you want to use, say, Google as a third data center to distribute your data. But Google don't give you that with Spanner. Amazon don't give you that with Aurora. None of these databases work to deal with this sort of challenge. So we've got different answers growing, different answers developing, but we haven't got the answer yet. So here's our fairy godmother. This is the only time the fairy godmother makes the appearance in the slides. There's a class emerging, and we know it's emerging because the hype cycle is starting to pick up. Gartner's just done a report which talks about assessing distributed SQL databases. And they are databases which are transactionally consistent, and so they're relational, they're transactionally consistent, relational like Oracle and those databases, transactionally consistent, unlike NoSQL databases, and then work at scale in the cloud and on-premise. There's kind of a shopping list of things that are interesting with these things. So without reading them all off here, I'm going to just talk about those sorts of features that you might want and why they're important. what are the requirements for that new data layer? So the first thing is about developer productivity with this. There are two aspects to this, and one of the driving forces is the Postgres API. Lots of databases now have the Postgres query layer. For those of you who may not know about this, most databases are written in two tiers. They're written as a query layer, which parses the language and handles what you're doing. And they're written as a storage layer, which writes the data. And one of the reasons Postgres has been so popular as a database and used by other vendors, so Infobryte, Netezza, Alloy have taken this, is the ability to take the Postgres query layer as open source and plug a different storage engine in at the back end. Now, the advantage of that is you've got tools. You've got a language which is familiar to your developers. You've got pgadmin to run it and look at the database. You've got extensions. You've got triggers, store procedures, PL SQL, all of these things which are really powerful. And it's interesting where you get to with this, because you have the idea that your security team, your CISO team, are familiar with Postgres. So they understand the roles and responsibilities, the RBAC side of it. They understand the PG audit. These things actually reduce the challenge that you face of putting in a database because it's familiar territory. And the second challenge is moving to the database for the developers. Because if you've got data in a legacy system, if it's Oracle and you want to change your varchar 2 to your varchar for Postgres, you need tooling. And the richness of Postgres tooling there to move from other databases to Postgres means that it's a viable migration, whereas moving to other APIs where there's no tooling becomes incredibly difficult for you. Let me just make a mess and spill it all over myself. So that's the first thing, developer productivity. The next area is elastic scalability. Scalability we all get. Scalability is the ability to add more nodes. And we can do that vertically, or we can do that horizontally. Vertically is simply adding more cores. Now, if I do that on a monolithic Postgres database, what I do is I shut the virtual machine down, change the VM underneath it, add 16 more cores, start the thing back up, and it's bigger. Great. So I've gone from 8 cores to 16 cores to 32 cores, 64 cores. Ooh, 128 cores machine, bit big. 256, 512. Yeah, starting to run out of these things. So the first problem is scaling up and down vertically. The second problem is scaling out horizontally, adding more nodes. There is no way that you can just have 6 nodes of Postgres doing the same thing as one database. That's the scalability side of it. So why have I focused on elastic scalability? Well, as one example of what happens, there is a day annually. It's a bit like Black Friday or Christmas. It's called China Singles Day. China Singles Day is actually the day more card transactions are done on the planet than any other day there. And it's a really weird thing, but in China, they buy presents for their single friends. They go on Alibaba, they spend a fortune. And it happens on the 11th of November, which is all the ones, and it's a completely marketing-driven event. There are banks which have databases to do the payment systems there, where they have the biggest Oracle Exadatas that they can possibly get, and the rest of the year, they occupy 1% busy. So you've got this massive Exadata, huge capital investment, sitting there, doing nothing. And then, for that one day only, because unlike Christmas and things where shopping ramps up and ramps back down, literally it's on that one day, the system hots up, you see it go red, works its way back down. That's expensive. That's the most expensive part. That's not a cloud-native approach to a database. What you want to do is scale it up a couple of days before, keep ramping it up with the volume, dynamically do that, and scale it back down. And so that elasticity of scalability is not, we do this with the application with stateful sets today in Kubernetes, but we don't do this with a database. We just can't afford to move it up and down in terms of size that easily. So I think that's another key feature of what we're looking at for databases. We also have to have system resilience. Now, that means that your database in CAP theorem has to be a CP database. You have to be consistent and transaction aware. So if you write to any node, it has to be written and communicate back that it is written. It can't have eventual consistency, because that doesn't give you your banking applications. So you build that transactionally consistent system, and there's something called a Jepson test, which allows you to test whether a distributed system is actually transactionally consistent. That gives you synchronous replication. Because it's now written to multiple nodes, it has to be synchronous and have committed back to those things. That means that if a node goes down, any other node can pick up the work and carry on going with it. But it also means that if you have multiple writers on there, you can write to many nodes. So because of this read-write to many nodes, what you get is the ability to scale the size of the connections that you're making to the database. Because if your Postgres node can handle 200 connections, and if you have a Postgres API and you're running it on a 6-node cluster, you can handle 1,200 connections. So your scalability of this and your resilience becomes really important. But there's another thing that comes out of having multiple nodes, and that's the ability to do rolling upgrades and to deal with rolling restarts. So, it's always a test question, but how many people avoid doing an upgrade because they don't want to take the outage? If you're on a 5.9 type system, we'll do this one because it's an important security patch, but we'll wait and skip that patch because we can't afford to do it. We don't want to take the outage to run this, all the little things that go into those failures. So it's not just about failure of the system, it's also about managing the uptime and availability for normal operations in terms of these things. So high resilience is another key feature that we're looking for. Operational efficiency. So the next challenge that you face once you started building these things is the ability to manage the data. If you're running a traditional database, what you're going to be doing is manually sharding. If you're trying to get to scale, you're going to be saying, right, what we're going to do is put this data here, put that data here, there. All of this embeds in cost to the organization. You have lots of DBAs looking at this work. You have lots of planning, modeling, and then the database changes. One of the most dramatic things that happens, and we see this time and again, I've seen it on both sides, both as a vendor and running systems, is that something unexpected happens. So you've got 15 microservices, 20 microservices, and you size them last year, you put in the budget, you put in the systems for them, and then something happened. Suddenly, what you were doing was on trend. And one microservice went ballistically popular, double resource, double capacity. And suddenly all the queries started going slow because the sharding that you'd done was for all the wrong region. Outage, panic, late nights, all reworking these sorts of things. Can't scale it without changing the sharding, can't get involved in these things. The next side is about the DevOps side of life. Because a lot of traditional databases are not written with DevOps in mind. So how do you change things in the database from a CI/CD pipeline? How do you update the configuration, restart it? How do you expand or dynamically control a cluster? How do you performance tune dynamically? All of these things can be addressed by having multiple nodes and then doing a rolling restart so that you can actually see how these things progress across the things. And a modern database can be written so that everything is done by an API, a CLI, or a UI with these things. So you can actually drive the whole thing from a DevOps environment. So you can actually build your dev test so that your test cycle goes, let me create the database, performance tune it to the latest metrics, run in the application, run the test suite, delete the database, come back in a Kubernetes cluster. And that has interesting cost implications as well, which I'll come on to in a moment. But if you think about this, if you're not running test environments which are built in big databases, if you can take them away again quickly in the cloud, it's going to be cheaper. Touched on rolling restarts and upgrades already. And then the other thing is a distributed system is inherently complex. You'll know this from tuning Kubernetes applications and things. What's the levels and things? So you need performance advisors within the system. You need to have things which tell you where the work is going, how you observe this, observability from the node status through the query layers, the storage layers. Because if it does get out of sync and you do need to see what's happening, you need all of that observability across all those lines. Security and compliance. One of the pet areas. But any database needs to be able to manage this at scale. Now, any new database. And it's surprising how many new databases throw away some aspects of this. So you need, because you can inherit the Postgres layer, you can actually manage authorization and authentication with the same tools that you use for Postgres. Encryption and tokenization is really important where you're holding personalized data, things like PCI data with those things. But then you have to manage encryption at rest and encryption in motion. And for any major system, for encryption in motion means all the nodes in a cluster have to be talking TLS 1.2 or more, just to be compliant with half a dozen regulations, HIPAA and FedRAMP and PCI and GDPR for protecting the data. All of these things feed into this life. But if you've got a distributed system, you also have to manage all that data at rest. So you want to tokenize it, and it's not sufficient to rely on the encryption of the disk from the cloud vendor. Because if you go across multiple clouds, you've got different tokenization keys and so on for the devices. So that, yeah.
Sorry, double question. Can you explain tokenization?
Right, so it's interesting, so you've got two layers with it. Tokenization is what you do, so encryption is how you, I'll give an example of credit card, probably the easiest way. Raw credit card number, that's fine. Encryption means you write it one way and it's reversible in terms of what it is, so you can decrypt it to find out what the value is. Tokenization is what you do where you write it and it gives you a surrogate for what you have, which is recomputable but not reversible. So in particular, you see this on your iPhone. You probably you're not aware of this, but you see this on the iPhone. Every time you use Apple Pay on your iPhone or Google Pay, the credit card number that you've got is actually a token. So they don't hold your credit card number on the system. They hold a token. Payment travels through the system with the token, goes to the bank, and they say, oh, we recognize that token. It actually maps to that credit card, which is why the payment systems are secure with these things. And if your phone is compromised, that token is includes stuff which matches to your phone, so it's actually impossible to use it elsewhere. So tokenization is a very important part of how systems are managed these days with these things. But yeah, a lot of it is a hash. It's a fancy way for hash, but yeah, there are other things you need to do, but fundamentally, SHA-256 is quite a good way to start your tokenization method. No. Did I see the thing? So you do those, but the encryption mode, the data rest encryption is also important. What you start to have with this is the idea of doing rolling keys. So it's great that you've got it encrypted, but then on a distributed system to manage all these things, you have to rotate the keys periodically. And so all of the systems actually have to manage how they do key rotation within these things, because if you have to change them every 28 days or every year or whatever it happens to be, then asking questions about how rolling encryption is done is absolutely critical to being able to deal with the systems. Ensure that the data is only stored in permitted locations. Now, I've started touching on this one, but imagine a system that you build where it is stored in one place but readable from somewhere else. So personal information has to be stored in the UK, So you need all of the data. You need to be able to basically partition the data automatically and say that UK data is in the UK, European data is in Europe. This is actually becoming more of a challenge for people. If you want to have, if you start thinking about what that means in terms of Kubernetes design and systems design, that means that the stateful sets for the database have to sit on nodes that are in UK. There have to be 3 of them to give you quorum. They have to sit in different data locations. And if you want to hold European data, they have to sit on 3 in Europe, but they have to be part of the same database instance. This suddenly becomes a huge requirement on understanding the data. And these things are becoming increasingly more important in terms of the design of systems. Storing it is one thing, but then accessing it from other places is there. So you may be allowed to read it from somewhere, but not store it somewhere. So it's valid to aggregate it, for example, from the UK, even if it's European data, but it's not valid to go the other way. So you actually need data management at 2 layers. One is where you store it, and also one is how you access it to deal with these things. And if you're thinking, right, this is a lot of technical detail and it doesn't apply yet to my system, the thing that's evolving is that this is coming all the time to people now. As industries change, these sorts of challenges are coming. There will be more, not less, going forward of these types of challenges in the data. Automated patching. Cybersecurity is important. You only have to see the number of data leaks. All of this stuff becomes more and more important. And as I've already touched on, which is right down at the bottom there, concentration risk, but I've already touched on that. Cost efficiencies. Here's a statement. Organizations can save up to 50% of their infrastructure cost if they shut down dev test overnight. So, as you can imagine, I've got a dev team working for me, and we were letting it run, and our Google and our Amazon and our Azure costs were spiraling up quite neatly. And then one of my engineers came to me and he said, "You're complaining about how many nodes we're running for our testing." He says, "Why aren't we using our own APIs?" I said, "What do you mean?" He said, "Well, we'll put a tag on the database which says that it's either 24/7 or a tag which says it's 9 till 5. And at night, if it's 9 to 5 at 7 o'clock, we give people a bit of grace because we don't want people just logging off. It goes around and it shuts all those databases down. And then it starts them up again in the morning for them. And shutting those down has halved our cost. We showed this to a couple of customers. And they said, yeah, we can do this with all of our databases too. If you can automate this, you can just take out cost of dealing with this. And then I touched on the China Singles Day example. And with the China Singles Day example, you also get this scaling up and scaling back down. So if you scale from, let's say, 3 nodes times 8 cores, your normal production, to a China Singles Day where you've got 128 cores, and you do that for a month, you will take out somewhere around 50% of that cost and 25% overall cost out of your systems. So cost management is another feature which you want out of the database. And then if you're going to run this at scale, you want this as DBaaS. You want it to look like Google or Azure or any of those services so that you can actually automate this. You want a familiar interface of the cloud service provider, but you want it in an agnostic way. And all of that comes to my most complex diagram on the world, which is that one. But on the left-hand side, you see everything that you need is a management side. At the bottom, I'm not planning because I've talked about all the features of this with it. But on the left-hand side, what you see is all the management features. At the bottom, you see all the different cloud services that you may want to run it in. And on the right-hand side, you see the tools that you're going to need to do these sorts of things. So building a modern database, which is going to support Kubernetes and things, is a challenge. But this evolving class of distributed SQL has come with this design philosophy to be built cloud natively, to have all of these features built in. So just 2 quick examples before I wrap up. See, she's got me timed on the back there, so the good thing. Here's your traditional Postgres example. This will feel desperately familiar. It's configuration managed in the application for the connection string there. A load balancer network team's involved in doing that. Connection pooling, because you need to get all those connections into it. And then a Postgres database, which is a single point of failure unless you've got some clever replication which you're manually configuring at the bottom end. If you take a multi-node distributed database, it becomes that. It becomes a database which has got inbuilt connection pooling, doesn't need a load balancer, has a smart driver which is topology aware. So every time you connect that driver up in the top right hand, it's the same Postgres driver, but it's got a topology wrapper around it, which allows it to understand where the nodes are. So one node goes down, it gets told to reconnect to a different node. All of that takes out multiple teams. This is now a service run by a DevOps team. Kubernetes has been built, or VMs, but whichever you're using, it's been built. They go to an API or a UI, they select the database type they want, where they want it, the scale, how they want it to operate. Press the button and they get that service. And that's a database, that's where database modernization needs to end with these sorts of things. It needs to end at that level of interaction. And a similar thing, just to talk about the traditional Oracle database at the bottom side is a Postgres example. What you can see is Golden Gate. You then need to have observer nodes. You need to have all this managed. You have a great DBA team. I'm sure they do sterling work around the place. Asymmetric setups are hard to manage. High availability is compromised because if you lose zone C, you don't know where your master is. Need to rebuild the data on a node failure. It's complex. It's not automatically doing it. That's what it looks like. Same configuration, same there. 3 nodes, 3 different zones, all read-write. That's what a distributed system gives you. And so, as I said at the beginning, I'm the field CTO for Yugabyte, so we have to have the inevitable plug side. Everything I've said at the start of this about being distributed systems is true of all of the distributed systems. There are many good technologies out of there. We're one. We're scalable Postgres. We're transactional. We're open source. We are built by people who've come out of Facebook and Cassandra to engineer this thing to be a scalable database for Kubernetes, VMs, and on-prem, and in the cloud. And with that, I'll take any questions, or you can run away. I promise no more mentions of Cinderella either. Hi. I've got the mic here. I ran away with the mic. And there's a gentleman in the back there, left-hand side. And I literally have never had somebody run away before. That was quite brave of him.
Hello. Yep. Thanks for the presentation. My name is Dan.
Hi, Dan.
So about the Chinese Singles Day example.
Yeah.
Let's say I'm a Chinese company like selling something.
Yeah.
And I usually have some database provisioned, but then for that day I need like 100 times my capacity or something. What if everybody does that? Like then what if AWS like doesn't have enough capacity to provide for everyone 100 times their usage? It doesn't matter what.
So
yeah.
One of the big US retailers has actually shopping retailers. So you know who they all are. They're all the big brand names you've ever heard. I can't tell you which one. Has actually made the decision to move for their Black Friday. They're now running it so that they run the majority of their data center for their core transactional system back on premise. And they're doing this for 2 reasons. One, the size of their systems is so huge that it's not it doesn't work with the cloud service providers, the premium that they're doing it. And the second thing is that they're scared about exactly what you're talking about, capacity. I also talked about concentration risk. So with concentration risk, one of the things that we can do, we can literally build a database with 1 node in Google, 1 node in Azure, 1 node in Amazon. So because you have that flexibility, you can now start to build those things. So Amazon's run out, but actually we can build it in a different region in Amazon. We can just extend the cluster. Or we can say, oh, well, God, you know, it's not a good day. Amazon's running out of capacity. Let's move some of that capacity to Google. And these are going to be the challenges. We're good at this, but the automation at scale for this is going to be the next challenge. You're going to have to buy cloud services like this, capacity on servers, you are, within 3 years, people will be talking about the importance of, because the regulators are already there, there are already legislation for this, they're going to be talking about how you scale between clouds, across clouds, all of those aspects with it, because of the sorts of contention risks. And there is a website called something like Amazon Failures, or Amazon Region Failures. You can go on it now, and you can see the number of failures per week across different zones and regions. So these issues, as the cloud's great, we've boomed into it, everything's gone there. The reality of mass usage is going to become more and more challenged. I also suspect that energy constraints are going to become a thing. If you have a blackout in the east coast of America and you lose North Virginia, you're going to lose an awful lot of services that you're used to just being there on the web. So, yeah, it is a challenge, but I think that's a universal challenge. And for us, what we're doing is building that in as part of cloud native design to be abstracted from that dependency.
Thank you.
Any more questions? Look at that, 2 minutes to go. Do I pass? Thank you very much, everybody.